So we started to do the global stability of Minkowski space. So this was the model problem on stability of Kerr in the axially symmetric case. So we discussed this. Right. So there was this conjecture. And then we discussed stability of Minkowski space. So let's recall very fast. So the main ideas on stability of Minkowski space is that you have decay, that perturbations radiate and decay sufficiently fast. And unlike in the case of black hole stability, all components of the curvature decay fast. Well, for example, if you want to deal with stability of the Kerr solution, you have components components of the original space-time, which is non-trivial, and that leads to all sorts of complicated, difficult problems, difficult to deal with problems. Then Bianchi identities as a Maxwell-like system, which we discussed. So this is an invariant way of treating the hyperbolic character of the equations. And then, of course, to get the decay and the energy estimates simultaneously, the idea is to get both simultaneously rather than decay usually was done, traditionally was done by Fourier methods or decompositions or the method of separation of variables, which is extremely costly in a nonlinear equation. So instead, what you want to do is to use this vector field approach, which allows you to treat both the energy and decay simultaneously. And then there is a null condition and a bootstrap argument, which is complicated. Okay, so then we went a little bit through the standard case of how to use the vector field method when you have to derive decay for the wave equation, for the Maxwell equation, and for the Weyl field. Right. So for the Weyl field in Minkowski space. So we showed how using energy estimates and commutation properties with certain vector fields in Minkowski space, which correspond to symmetries, you get the full decay of the components of the Weyl field, right? So these are the sort of things that we discussed last time. Okay, so then we went to the actual stability of Minkowski space. The setting was so the setting here was that you start up at sigma 0 and you construct space-time together with a foliation which is maximal. So maximal means that if I look at the second fundamental form here of the foliation, trace of k is equal to 0. So trace of k relative to the induced metric. So here you have g and k, the induced metric. So you have a space-time metric and which you are constructing, which is so this verifies the Einstein equation equal to 0, and you construct the space-time together with the foliation. In the foliation, you have the induced metric, which is Riemannian, because sigma t is also maximal and space-like. So this is Riemannian. Therefore, I can talk, in particular, I can talk about the trace relative to the metric g of k. That should be 0. So that fixes this foliation. And you want, obviously, you want to construct this for all time as t goes to infinity. Okay, so asymptotic flatness, of course, we discussed. And of course, the flat initial data set. So what you want to perturb is flat initial data set, which is, of course, just delta and 0. So the metric is a Euclidean metric, and the second fundamental form is 0. You perturb it, solving the constraint equations. And of course, you have to also make a smallness assumption. Smallness So this is a non-trivial assumption which involves up to 4 derivatives of the metric and 3 derivatives of the second fundamental form on the initial data set with weights, the weights coming from the vector fields which you are constructing. So you construct a series of vector fields. So the spacetime is constructed, in fact, so given initial data set, which verifies a smallness assumption, you construct the spacetime, you construct sigma t, but more importantly, you construct a family of null hypersurfaces, u equal constant, which are normalized at infinity. So they are coming from infinity, they are coming inside. Okay. Right. So this is very, very important in order to get the correct decay along null hypersurfaces. All right. And then somehow in the interior, so once you have these hypersurfaces, these are null hypersurfaces Cu, so these are, then you can look at the intersection of sigma t, you call that S of t and u, which are 2 surfaces. Here you can define an R function, which is normalized such that 2 pi r squared, 4 pi r squared is exactly the area of STU. So this is how you define the R function. So now you have functions t, r, and u. U, however, is not defined everywhere. So I can define u in the region r larger than t over 2. But as you approach the inner region here, the inner core, the u function may actually form, may be badly behaved. In fact, it can form caustics and so on and so forth. So you really want inside, in the interior, for the region r less than t over 2, you want to construct a different solution of the eikonal equation. By the way, u verifies the eikonal equation, right? So u verifies the equation d alpha u d beta u, which of course gives you the characteristics, the conical characteristics of the spacetime, right? So in Minkowski space, these are just the line cons. In Minkowski space, these are just the line cons t is equal to absolute t minus absolute value of x, or t minus r rather, is equal to a constant, right? So, so these are the outgoing light cons. But these outgoing light cons don't behave very well in the region where r is less than t over 2. So if r is less than t over 2, which makes sense, I can define all these things. I want to define a different optical function, which is normalized. In other words, it starts, the initial data of this new optical function starts on the axis. So this corresponds roughly to r equal 0, actually. It's not exactly here what r equals 0 means, but it's a region where r is bounded, and therefore you can define an axis and so on and so forth. So this is also a complication which I didn't discuss last time, because it's not fundamental somehow. It's important technically, because you want to cover the whole spacetime by an optical function. But because somehow in the interior regions of r less than t over 2, the curvature tensor, all the components of the curvature tensor decay very fast. In fact, they decay like t to the minus 7/2. And there is no difference between different components. Because of this, somehow, what you do here is a little bit less important. But of course, you have to do it. And then somehow, you also have to put together the two optical functions. So there is a matching that goes on, which is also rather technical. OK, so anyway, so these are the things that you have to do. You look at the maximal global hyperbolic development. So these are model problems. So you compare, as I said, it pays to compare the stability of Minkowski space with simpler problems, like for example, the one which I discussed last time, which is a wave operator equal to n, a nonlinear function of phi and derivatives of phi. Right? So these are things we discussed last time. The null structure of n is very important. By the way, where do I have the pointer? You don't have it anymore, I guess. Right? There is no pointer. Too bad. Okay. Anyway, so the null structure of n is very important if you are in 3+1 dimension, because otherwise you can have global. You can have global. I mean, you may not have global solutions. You may have blow up, as we discussed. There are examples where if the null condition here is not verified, then you get into trouble. This is control this type of equations for small data in 3+1 dimension. If the null condition is verified, then you get the result by using the global existence result by using commuting vector field method, generalized energy, as we have already discussed. This global Sobolev inequalities, decay, null frames, null condition, and so on and so forth. So thank you. Yeah, that's fine. Thanks. Okay. Now, of course, if you go to the Einstein equations, you have, in addition to all these difficulties that come up in this problem, you have many others, like, for example, the fact that the problem of coordinates is a huge problem. In fact, in standard coordinates, the null condition is not even verified, as we discussed. There is another result of Lindblad and Rodniansky, which uses wave coordinates, in which case the null condition is not verified, but something which is called the weak null condition is verified. So you have no killing of conformal. So here you use, of course, because you are in Minkowski space, this is the wave operator in Minkowski space, you can use the vector fields of Minkowski space. Here, of course, you don't have, so you have to modify them. Right. Okay. So then we discussed the central idea, the fact that you start up with the Bianchi identities, and you treat them as a val as the Bianchi equations in Minkowski space. So in a first approximation, you assume that the metric here is a Minkowski metric, and then you do essentially the same thing as you did for the Weil equations. But of course, now you have to take into account the fact that the vector fields, you don't have good vector fields because you are obviously you are in a perturbed situation. So there are no killing and conformal killing vector fields. But you construct vector fields which are approximate killing and conformal killing, which means that the deformation tensor is sufficiently small, in, of course, in a way which you have to control precisely how small this is, right? Okay, so then these are things we discussed, maximal foliation, adapted null frames. So again, using this STU, you can define null frames. So as we discussed last time, given a two surface here, STU, and of course, you have the light cone coming from it, which corresponds to E equal constant. And you can construct a vector field here, which we called L, and also E4, and another one, which is transversal, which we call E3. Okay? And the way you construct E3 is that it's G3 E4 should be -2. They are both null, so both E3 and E4 are null vector fields. This is automatically null because it's tangent to a null hypersurface in the direction of generators, and E3 by construction. And of course, both E3 and E4 should be orthogonal to this STU, right? Okay, so and then of course you have a frame also, a null frame, which is E3, E4, and then EA is 1, 2. So these are vector fields here, which are tangent to these two surfaces. Yeah, so this is the null frame, and of course the null frame, as we discussed last time, plays a fundamental role. Then you define this global energy quantity, assuming the boundedness of this quantity, which of course has to be defined, then you can get the full decay estimates for the curvature tensor. So this quantity is very similar to the quantity in linearized case. And somehow this step is essentially the same as in linear theory. Of course, the problem is that now when you look at the equation, for example, this one, the Bianchi identities. And of course, you have also this one, the delta R alpha beta gamma delta equal to 0. So these equations are exactly satisfied, but when I commute with a vector field, which of course these are vector fields that have to be constructed, but in principle you think that they are not too different from the ones of Minkowski space. The main difficulty of course now comes that when you commute, you get equations for Lie x of R. So you get the same kind of, let's say, this one, the gamma delta. But now you have deformation tensors. You have terms which involve the deformation tensor. In other words, the Lie derivative. So pi, I recall, is the Lie derivative of the metric. So you have terms like pi times derivative of curvature plus derivative of pi times curvature. And these, of course, are extremely dangerous, right? Because now you have to do hyperbolic estimates with a right-hand side. So unlike in the Minkowskian case, in the flat case, you have to deal with these error terms, which are extremely complicated. And this is where the main difficulty lies. You have to treat the error terms. And in order to treat them, you have to have very good decay properties for all components of pi, all components of derivative of curvature, all components of curvature, all components of derivative of curvature. So, just verifying this, that this is okay, after you understand how each one term should behave, takes a lot of algebra. So this is sort of, it's not just analysis, but also a lot of algebra involved. Okay, so this is again what we discussed last time. So, okay, so the main quantity, so in other words, the quantity that already can be defined in linearized theory, of course, based on the vector fields of Minkowski space, which now obviously have to be modified, leads to an identity like this, where Q is the main quantity is equal to Q of 0 plus a space-time integral involving exactly the terms that I mentioned here on the right-hand side. Okay, so then that's a theorem we discussed, maximal foliation. Okay, so now I recall that when you construct the space-time, you have to construct with all these structures. Otherwise, any one of these structures is essential in the proof of the theorem. If you don't have, you cannot prove the theorem. You have the components of the curvature, which are defined exactly like in linear theory based on the null frame. So the null frame, of course, is a correct null frame in curved spacetime in the actual perturbation theory. But the behavior of the components of the curvature tensor are very similar to the one of the Minkowski space. In fact, the only difference is that this term rho behaves only like r to the minus 3, while sigma, which is similar to rho, and in Minkowskian theory they behave the same way. In flat space they behave in the same way. Now this term has the worse behavior because of the mass at space like infinity. Okay, so the mass is non-trivial in nonlinear theory, and it leads to this lower decay. But otherwise, the decay is very similar to the one in Minkowski space. All right, main energy quantity again. This is what I discussed. This is how it's defined. Of course, you see that you have to take Lie derivative relative to various vector fields. So you have to define this T0. You have to define this O. K0, K0, K0. Again, all these vector fields made sense in Minkowski space, but now they had to be modified. And the quantity, however, is defined exactly like in flat space. So the vector fields, of course, have to be defined. And as we discussed last time, they are defined by using the geometric foliations that we have introduced. In other words, you are using sigma t and you're using the null con Cu, right? And of course, you are using the intersections and the frames, right? So it turns out that all the vector fields can be defined naturally based on these geometric constructions, okay? So they are defined in such a way that they correspond exactly to the corresponding definition in Minkowski space, in flat space. Okay? The angular momentum operators are a little bit more difficult to define. So here is how K naught and S naught have been defined. So U, of course, is defined from the optical function, and U bar is just U. So U bar is defined from U and T, so that in Minkowski space this looks like T minus R, this looks like T plus R, and it's clearly that using a combination of U and T you get something which is similar to T plus R. Okay, so so these are T0 is just the uninormal to sigma T. That's natural, right? So you just take the uninormal. So this is d over dt. But I should call it T, capital T, is a normalized normal to sigma T, future normal to sigma T. It's a unit normal. S0 can be defined using U bar, U, L, and L bar, just like in Minkowski space. So this formula, so in Minkowski space, S0 is just T dt plus R dr. And you can easily see that it can be written as 1/2 U bar L plus UL bar, right? Where U and U bar are exactly T minus R and T plus R, and L and L bar are defined in terms of the natural. So this, in Minkowski space, this is dt plus dr, and this is dt minus dr. Right? Okay, so K naught is defined similarly by putting, in fact, U bar squared L plus U squared L bar. So K naught, I recall, in Minkowski space is T squared plus R squared dt plus 2T dr, 2T R dr. And again, it can be easily seen that it can be written in terms of that combination. And since I have a U bar defined now in my spacetime, the general spacetime, then these vector fields obviously make sense. The angular momentum operators are a little bit more difficult to define. They are defined by transport equations coming from infinity. I think it's not absolutely necessary now. I think you can use better technology nowadays, but anyway, this is the way it was done at the time. So this is the optical function that I discussed, U. These are the operators L and L bar. This is what happens in Minkowski space. These are the operators in Minkowski space, right? Right, so these are the angular momentum operators, look like this. Of course, you see angular momentum operators depend more on coordinates. So they cannot be defined just in terms of U and U bar, L and L bar. And that's why you have to bring them from infinity, okay? Because I don't have coordinates. We are not using coordinates here. We are using just foliation, right? The only thing we are using is U and T. So in other words, you are using, in fact, only two coordinates if you want to specify two geometric type of coordinates. All right, so these are the main commutation formula again, right? So if you take a Lie derivative of curvature relative to a vector field, this is what you get. It's a complicated expression on the right-hand side. And then if you look at the Bell-Robinson tensor associated to W, we discussed this Bell-Robinson tensor. There is an energy momentum. It's an energy momentum tensor, energy momentum-like tensor, similar to the one of the Maxwell equation, but having now 4 indices. Anyway, so you do all the natural things, but of course the formulas now are very involved. So the error terms, obviously in flat space, all these things on the right-hand side will be 0, right? And that's what makes it very easy. But here, of course, you have to deal with all those error terms. Okay, a main differential inequality again. Q of t is Q of 0 plus an error. The error looks roughly like this: curvature times pi hat. In fact, you can have derivatives of r, derivatives of pi hat. You can have Lie derivatives with respect to various vector fields and so on and so on. So this is just a very simple, compact way of expressing something which is a huge term here, right? Which has lots of components. So in fact, R denotes curvature components, including derivatives, and pi refers to Lie derivative of the metric relative to these vector fields which have been constructed. And of course, I can also take derivatives of those. I should, because Q involves many derivatives. Okay, so the naive estimate leads you into trouble. It's very easy to see that you get a logarithmic divergence. At the best, you get a logarithmic divergence. It can get even worse, but at best that you can hope, if you are naive and you are not using the full structure of the equations, you just get O of t to the minus 1, which is, of course, divergent. So in order to really control this term and show that it's bounded, you have to start decomposing all components of this, and use the fact that various components behave differently. And the worst component that should give you t to the minus 1 is never present, because whenever you have a bad component of one of these three terms, it always comes together with a good component, right? So that's where essentially what the null condition is all about. Okay, so this is how you get that if the initial data is sufficiently small, so this is Q at time 0, then it stays small for all time. And using this, you can get everything else. Okay, so now, as I discussed last time, you have to estimate the curvature tensor and Lie derivative relative to various Lie derivatives of the curvature. And this part somehow we understand reasonably well, right? It's very much like in linearized theory. In fact, this part is rather linear, except for the error terms that you generate on the right-hand side. So this is somehow more sort of to be expected if you understand well linearized theory. What is more complicated now is how you estimate the pi's. Right? How do you estimate the deformation tensors of these vector fields? And as I said last time, the pi depends on derivatives of t, derivatives of u. I mean, of course, many derivatives. Many derivatives of t, many derivatives of u, because I have to take not only the pi, but I have to take, yeah, so if I take just the pi, I need a Hessian here, for example. But if I take derivatives of pi, I need higher derivative of these terms, right? So the question is, okay, so this can be controlled in terms of these two, right? So then the question is, how do you control these ones? Okay. So this one is a Hessian of the space-like hypersurface. This leads to elliptic equations, roughly, right? So in other words, if you control already the curvature, the space-time curvature tensor, everything that refers to the Hessian of t, which means essentially derivatives of k, can be controlled by elliptic theory just on this hypersurface. Okay? Right? So there will be equations like, for example, I don't know, divergence of k and curl of k is equal to curve. So the divergence of k, so this is equal to something involving curvature. So for example, this well, let me write it in both cases, curvature. So somehow if I control curvature, which I control by the energy estimates, then K is controlled in terms of curvature by using an elliptic system. This is so trace, also trace K equals 0. This is an elliptic system, and therefore it gives me control of K. So this is not too hard. Everything elliptic is much easier, right? So you know, whenever you see something elliptic, you are very happy. This one, of course, is much more difficult. So this is much more difficult because it leads to transport equation. So this is a part that I'm going to discuss today in more details, in fact, because it's something very important that comes up in many situations. So I'll discuss how to treat the Hessian of U with, in more details. Okay, so in fact, we started to say last time that the Hessian of U is actually tied to the Ricci coefficient. So this is tied to the Ricci coefficient of this frame that we constructed. So remember that we have the frame E3, which we called L bar also. I guess, how do I call it here? L bar, right? L bar, E4, which I called L, right? And then E1, E2, which are tangent to STU, right? Okay, so these are the Ricci coefficients. And from the Ricci coefficients, I can define the null second fundamental form, chi, which is an extremely important quantity. So this is a tensor. In fact, they are all tensors defined at a fixed T and U. They are defined on these surfaces, S of T and U, right? So chi is a tensor, is a two tensor on that surface, defined like this, where X and Y are tangent to the to this STU. Zeta is a derivative of L in the direction of X, which is tangent to STU, and L bar, and so on and so forth. So you define, I'll discuss it in more detail later on. Okay, so, right, here I didn't say what N and K are. Anyway, the K and the laps are associated to this T foliation, and they lead to elliptic estimates, as I have already said. But this one have to be, so A is something, actually here I call it A, later on I'll call it, this one is in fact what I call omega bar later on. But anyway, for the moment you can take it as A. And so the question is how to define this. So we'll talk a lot today about these kind of equations because they come up in many problems. But in a first approximation, you already see that this component chi verifies a so-called Ricciarduri equation, which looks like this. D over ds chi plus chi squared is minus alpha. So alpha is a component of the curvature tensor. So alpha is, in fact, actually, I don't know if I define it here. I think it was defined later on, but let me write it. Maybe I should erase this. Okay, so we have the frame, L bar, E1, E2, right? These are the EAs. And we define the Ricci coefficients. Which are derivatives of the frame relative to the frame itself, right? So this is the standard. You take covariant derivative of all these quantities and you refer it to the same frame, and that's how you get the Ricci coefficients. And then you also define these quantities, which we had earlier. So alpha AB is REA L EB L. Okay, so it's a component of the curvature tensor relative to the frame. And it's not too difficult to derive this equation, that d over ds of chi plus chi squared is equal to minus alpha, where S is an affine parameter associated to Z. So L of S is 1. Right? So it's just a parameter associated to the vector field L, and L itself is very geometric. L is a generator of these null hypersurfaces, right? So in fact, L, I'll write it again, L is minus 1/2. So minus actually G alpha beta D alpha of u. So it's this vector field, right? In other words, the gradient of u with respect to the metric. And this is a famous Ricciarduri equation. D over ds chi plus chi squared is equal to minus alpha. So this is a two tensor. It's a two tensor. So it's chi times chi in the sense of matrices is equal to alpha on the right hand side, which is also a two tensor. By the way, alpha, the trace of alpha is 0. It's easy to see. This is a consequence of the Einstein equations. Einstein. Right? In other words, the fact that Ricci is equal to 0. Okay, so you see that if I control alpha, in principle, all I have to do is solve an ODE. Right? And that's what's done. Of course, this is a bad ODE because it's like a Riccati type equation. So you have to do a few things. It's not so easy, but that's the idea. The idea is that somehow, once I control curvature, everything else connected with this Hessian of u, right? Remember that we had Hessian of u, Hessian of t. Everything here was elliptic. Everything here is ODEs, but not quite. Actually, there is more than this. There are also elliptic equations on STU. Okay, so in other words, the curvature is obtained by hyperbolic estimate. So curvature is hyperbolic, R hyperbolic estimates. In other words, energy estimates and everything that we discussed that has to do with the vector field method. And then the Hessian of t is elliptic. Hessian of u is ODEs and maybe elliptic equations on two surfaces. See, here it's elliptic in the sense of 3D elliptic, right? So it's elliptic on this entire space-like hypersurface, while here it's elliptic on these two spheres, right? Okay, so that's roughly how this goes. So anyway, so this is everything leads to these grand bootstrap or continuity arguments. You make assumptions about everything, and then you improve everything, right? Okay. But you have to make assumptions on all components. So you have to make assumptions on all components of the curvature, all components of these Hessians, and of course all components of the pi's. In fact, only the pi's come in. In the main estimates, only the pi's come in. This one are only used to determine the pi's, right? Okay, so these are the initial data, asymptotic flatness, and so on and so forth. I mean, here I'm just repeating. These are now the vector fields. So this is just a repetition of what we had before. But now you know what the vector fields are. And you also know, right. Okay, so anyway, so this is basically what I discussed last time. All right, so now what also can be done, and I'll discuss maybe a little bit, is a different approach. It's a different approach, but it doesn't give you the same result. It gives you a little less in a way, but it's useful from other points of view. So there is a companion result which was obtained later, I think in 2003 by myself and Nicolo, in which again you look at the initial data sets. You look at sigma jk, a general initial data set. It satisfies the constraint equation and it's asymptotically flat, exactly like in the stability of Minkowski space. But now I don't make any smallness assumptions. Instead, I look outside a sufficiently large compact set on the initial data. Now, since the initial data is asymptotically flat, outside a sufficiently large compact set, it becomes small. So the smallness will be sort of automatically satisfied in some sense. And then the idea is to construct a solution in the complement of the domain of dependence of this initial data set. I mean, this compact set, sorry, on the initial data. So in other words, you construct the spacetime here and here. Right? So this is the result. And what's important about this result is that it's done differently than here. You are not using maximal foliation. Instead, you are using a doubly null foliation. So you are constructing, right? So starting with this boundary, which is, as I said, it's a boundary of the domain of influence. I guess this is called domain of influence, right? Yeah, that's a domain of influence. Domain of influence of the initial of this compact set. So you're starting up with this boundary, and then which will correspond maybe to u equals 0 or something. And then you construct null cons exactly like in that case. So you construct an optical function exactly like before. So a foliation by optical function. But now instead of having a t function, you construct a foliation in the opposite direction. So you construct a u bar foliation. Right? So now you have two optical functions, u and u bar. Right? They both satisfy the iconal equation. But of course, one is defined to be outgoing and the other one incoming. Of course, the difference is in the initial data, the way you initialize the conditions, right? So again, the u here, which is a more important one, is initialized from infinity. So it will be initialized at scry, in fact, right? Of course, how you do it, you don't have the scry to start with, right? So the idea is to, in fact, I didn't explain, I should have explained it even here. The way the bootstrap works is that you assume that the spacetime has been constructed up to a time t, and then you use this t as sort of your last slice and construct the optical function from here, from this last slice. Okay? And then you extend the spacetime. And therefore, by a continuity argument, you show that the spacetime can be continued forever. So the same thing here. You have a last slice, right? You construct the spacetime here. By bootstrap, you assume that you have the spacetime controlled all the way up to here, and then you extend the spacetime by doing all the estimates, all the machinery. So this is the last slice, and then so this is u bar now. So u bar star will correspond to the last slice, and then you have u bar here, the foliation in the incoming direction. So what's different is that everything that I said before, before we had t and u, and the Hessian of t was obtained by elliptic estimates. If I already know the curvature, so if I already know the curvature, okay. So now you'll ask me, well, but the curvature in this case was estimated on space-like hypersurfaces because the energy is always defined on a space-like hypersurface. It turns out that it makes no difference. You can see that already in Minkowski space. So you can even assume that you are in Minkowski space, and you are studying this equation, d delta r alpha beta gamma delta. Right? So this is a Wald field, or Maxwell equation if you want, or any of the linear equations. You don't have to use a space-like foliation. You can use instead the foliation given by u and u bar. So somehow all the information that you get on sigma t is included in information on both null hypersurfaces. If I use only one null hypersurface, I lose information. But if I use both, I don't. Right? So that's sort of the philosophy. Okay, so let me go very fast over this. Okay, so actually, Niccolò and I proved a stronger result. than the one in the stability of the Minkowski space in the following sense. We showed, of course, you can make assumptions about G and K which are similar to the ones we use in the stability of Minkowski space. In other words, you make asymptotically flat assumptions of the same type, and then you will get a same kind of results insofar as the decay of the curvature tensor is concerned. Okay, so the curvature tensor will behave in the same, so the pinning properties will be the same. So remember the pinning properties, we had them here. Yeah, here. So these are, think of R being like T. So these were the pinning properties. As you see, here you have only -7.5. If somehow the Penrose compactification, which I didn't discuss, but maybe I'll mention now, so Penrose proposed, way before the stability of Minkowski space, Penrose proposed a way of reading the decay properties of the curvature by making an assumption that the spacetime can be compactified in a smooth fashion. So this conformal compactification was supposed to be smooth. If you make that assumption, you can derive similar pinning properties, in fact stronger. So because of the fact that the spacetime, the conformal compactification, in other words, the boundary that you add at null infinity, was supposed to be smooth, you would get here r to the -5, r to the -4, r to the -3, r to the -2, and r to the -1. Okay? And as you see, these components are behaving much less than in the conformal compactification. So the conformal compactification gives you stronger decay, which means that somehow the stability of Minkowski space that we proved, this version, does not necessarily assume smoothness of scry. In fact, scry is not going to be smooth. It's going to be rough. Okay? So and that's why one of the reasons why people who have tried to use conformal compactification to prove the stability of Minkowski space always failed because the boundary at infinity scry is not a smooth boundary. So you cannot really do the sort of things that people were doing without paying the price of having singularities introduced in the equation. So in any case, this is the pinning property. Now, in the result of, so as I said, so remember that this should be r -5, this should be r -4. In the results that I obtained with Niccolò, I said we can do a little bit better. So here is what it is. Assume that the initial data, if you take away the Schwarzschild part of the metric, the Schwarzschild part of the metric is 1 plus 2m over r, 1 minus 2m over r at infinity. So if you subtract the Schwarzschild value, which in other words, what it means is that you subtracted the mass term, which decays only like 1 over r, then in principle the rest should behave better. Now how much better? It's sort of up to you. Naturally, in the stability of the Minkowski space, I wanted to have only r to the -3/2 here. Remember that this Q means how many derivatives you are taking. So every time I take a derivative, I improve the asymptotic behavior, right? Okay, but you see now I'm making a stronger assumption. I assume that after I take Schwarzschild part out, I cannot do anything better for the Schwarzschild part because it's m over r. So I cannot assume all of a sudden that I get better decay than m over r. But I can subtract, if I subtract it, I can allow better behavior here. Of course, it's not going to be generic, but it's interesting to see what it gives you. So it turns out that if you take gamma to be larger than 3 over 2, right? In other words, you get much stronger decay here. Q refers to how many derivatives you take. Then, in fact, you get alpha to behave like r to the -5 and beta behave like r to the -4. So you get the peeling by essentially the same methods. I mean, you have to work a little bit harder, but not much harder. I mean, you have to work a little bit harder because you have to introduce this. In addition to all the norms that were introduced before, you have to introduce this u to a power in the, so weights relative to u in the main energy norms. So that's u to the gamma, so gamma is exactly this gamma here. So it's, it turns out that somehow this gives you additional information. Okay, you also see here that you have now two quantities, while before I had only one quantity, which was this q of t. Right? There was this q of t, which was an integral on sigma t. This was an integral of sigma t of various components of the curvature. Here I have two quantities, one on cu. So cu is, of course, in this picture, this is, of course, cu, and this is cu bar. Okay, so this is the outgoing, and this is the incoming one, right? So I introduced two energy type norms. Actually, they are fluxes now because they are integrated along null hypersurfaces. So you are introducing two flux terms, Q1. Well, one means that I take only one derivative. Two will be that I take two derivatives, and so on. So you see, this is integrating along Cu. This is integrating along Cu bar. Right? So, and of course, I have to do something at the higher level. I have to take also two derivatives. One derivative is not enough. One derivative refers to how many Lie derivatives I take relative to my vector fields. The vector fields can be defined in a very similar fashion, just like before. Instead of using T and U, now you use U and U bar. Right? So using just U and U bar, I can define all the vector fields, T, S0, K, K naught, and so on. Okay? And these omegas. Sorry, O. I guess I call them these angular momentum operators. So, but otherwise you do essentially it's the same thing. The only new thing is that you are integrating along these null hypersurfaces and that you are putting these weights here in order to get a better result. Okay. Now, this leads me to the doubly null foliation. So why doubly null foliation? Because somehow the energy norms are treated a little bit different from before, but not much different. Sorry. Right? So we discussed in the case of stability of Minkowski space how the Q norm should be treated. Well, it turns out that these are not much different, right? And they keep track of different parts, different decay properties of various components of the curvature tensor. So this part, in a sense, is slightly more complicated than before because you have two characteristic directions, and you have to somehow jungle the two. I mean, sort of go back and forth between one and the other, and you have to do it correctly. So in some sense, that part is slightly more complicated. On the other hand, how you get the pi's is now much easier. Right? So we have to go the deformation tensor of these vector fields. So pi of the vector fields which are here. And as remember, in that time, in this case, they depended on the Hessian of t and the Hessian of u. Right? Now they will depend on the Hessian of dt and d2 u bar. Right? And this is now much more symmetric because, you know, I do something for u and then I do something for u bar. So somehow you gain in symmetry, while before these two things were treated very differently. So the Hessian of t, of course, was elliptic estimates, as we discussed, while the Hessian of u was transport equations. So now you treat both of them by transport equations. Okay, so that's sort of the major difference. So this is called the doubly null foliation. So what I have here, a foliation by u and u bar, is called the doubly null foliation. And again, doubly null foliations are extremely useful if you remember that in the talks of Da Fermos, Jonathan, and also Holzegel, they were all using double null foliation. So double null foliation is sort of the foliation of choice nowadays, right? So I thought that maybe we'll go a little bit more into it. Okay, so So this is the situation. I have two optical functions, u and u bar. They verify this type of equations. I define the geodesic vector field associated to u and the geodesic vector field associated to u bar. So of course, one of the beauty of this double null foliation is that you have a symmetry between bar and unbar quantities, as we shall see, because L and L bar are now defined in a symmetric fashion. Okay, so this L and L bar are geodesic vector fields. It's easy to see. Geodesic means that maybe I should erase again. Okay, so we have L and L bar, right? So this is minus G d alpha of u d beta. So this is the vector field associated to u, and that's the same type of expression associated to u bar. So these are satisfies the diagonal equation, and because they satisfy the diagonal equation, it's very easy to see that dLL is 0 is dL bar L bar, right? And that both are null. So GLL is GL bar L bar equals 0. So this follows immediately from the diagonal equation, from the fact that u and u bar verify the diagonal equation. All right, so then you define this omega as being essentially the angle between L and L bar, right? So in Minkowski space, the angle between L and L bar is exactly -2. So in other words, omega is 1, I guess, in that case. Sorry, omega would be 1. Okay, so exactly in Minkowski space, omega is 1. Okay, now you define the null pair to be omega, so you normalize L bar and you normalize L by the same kind of omega. Now, in different situations, you want to make different normalization, but this is the most symmetric normalization when you take E3 is omega L bar and E4 is omega L. And now you have that E3 and E4 are equal to -2. In other words, E3, E4 is now a null pair. They are both null and null pair. Of course, they are not geodesic anymore, right? Because L and L bar were geodesic, but not these ones. But that doesn't matter. And now you define the Ricci coefficients. So Ricci coefficients are defined in general by taking the covariant derivative of the frame relative to itself, right? And defining these gammas, which depend, of course, on lambda, nu, and mu, which are lambda, mu, and nu go from 1, 2, 3, and 4. And then among all these Ricci coefficients, you distinguish the important ones, which are chi, which we already have seen, which is a null second fundamental form. So it's defined as dA E4 EB, chi bar, dA E3 EB. So again, you see the symmetry between chi and chi bar. You go from E4 to E3. Eta, which is defined using D3 of E4 EA, D4 of E3. Omega, which is G E3 D4 E4. So D4 E4 is not 0 because of the fact that because of the normalization. So this is not 0, but it's actually easy to see that it's defined in terms of derivatives with respect to E4. This is the derivative with respect to E4 of log omega. And omega bar similarly is defined in this fashion, and it's minus the derivative with respect to E3 of log omega. Right? Okay, so those are very easy. You also see here, theta, I guess, is missing here. Theta, there is also theta, which is G of dA E4 E3. Right? So that's the other possible component And it's easy to see because, again, because of the way the frame was defined, that eta plus eta bar is equal to 2. These are angular derivatives. So in other words, these are eta depends. So this should be written like this. Eta A plus eta bar A is EA of log omega. Right? So it's in fact a 2, I guess. Right? So that's the meaning of this expression here. And eta minus eta bar, it's also easily seen that it's equal to zeta, right? So in other words, there are some relations between the Ricci coefficients. Okay, so that's, what time is it? Oh, it's already 3. Okay, I didn't realize. Yeah, so that's maybe a good time to stop. So I'll change gears a little bit. We'll still talk about the double null foliation, but now in the context of this formation of trapped surfaces issue. So again, this is the double null foliation that we already discussed. So 2 optical function, this intersection between u equal constant, u bar equal constant, the geodesic vector fields L and L bar, the angle omega squared defined like this. Omega is 1 in Minkowski space for the standard double null foliation. The null pair, which is normalized in a symmetric fashion, right? And once I have E3, E4, I can also define E1 and D2, right? So, oh, sorry. So I can also define E1 and D2 as being tangent to the surfaces S of u, u bar. Okay. So now I have E3, E4, E1, E2, just like in the stability of Minkowski space. We have the Ricci coefficients, all the Ricci coefficients here. And then we define chi AB, chi bar, eta, eta bar, zeta, which is half dA4 E3, omega, omega bar. And we see that omega and omega bar are defined in terms of omega. This derivative here is just the E4 derivative. And this is a E3 derivative. And you also have eta plus eta bar is this quantity, derivative of, so this is the angular derivative here. And then eta minus eta bar is 2 zeta. Okay? So these are all the relations that you get for a general double null foliation in space-time. Okay, so now you also define now the components of the curvature exactly like before. So alpha has 2 E4s, alpha bar has 2 E3. So this is symmetric to this one by interchanging E4 and E3. Beta bar, observe that if I interchange now E3 with E4, I get minus beta bar. So if I interchange E4 with E3, I get alpha bar. But here there is a change, which is you have to be careful. Beta goes into minus beta bar by symmetry. And here rho is E3, E4, E4, E3. And rho star, which is sometimes called sigma, is R star, so the Hodge dual, E4, E3, E4, E3. Okay, so that's how it goes. Okay, so now the idea is to relate, the Ricci coefficients to curvature. So as we know, derivative minus derivative plus gamma times gamma minus gamma times gamma in various combination of indices here, it gives you the curvature tensor. So in other words, I can express components of the curvature relative to the frame in terms of derivatives of the frame, right? So derivative of the frame coefficients. So this is what you get here. And you observe that you get 2 types of transport equations. You get a transport equation of a Ricci coefficient. Okay. So you get a transport equation of a Ricci coefficient in the direction of E4. So this is a derivative of a Ricci coefficient in the E4 direction is equal to a curvature component. This is an angular derivative component of some gamma. In other words, not necessarily the same gamma. And then you have some gamma times gamma, again, not necessarily the same gammas, of course, right? So this is a matrix type equation. And you have a similar one, which is symmetric by interchanging E3 and E4. So these are the null structure equations, the transport part of the null structure equations. So they are equations, the way to think about them is that they are equations in the E3 and E4 directions, right? So this is, if this is my doubly null foliation, this is in the direction of E3, this is in the direction of E4, right? So you have ordinary differential equation along geodesics going this way, null geodesics going this way, and ordinary differential equations along null geodesics going this way, right? So these are the ones expressed here. Okay, so there is another kind of equation which is very important, which is a Kodazzi type equation that we will see, which gives you an angular derivative of a gamma expressed in terms of curvature plus another combination of gammas. And this is an equation which is intrinsic to this SUU bar, right? So that's okay. Then there is another equation which is very important, which is a Gauss equation, which relates the Gauss curvature of one of these surfaces, S of UU bar. So you look at the induced metric here, you look at the curvature of the induced metric, and you find that the curvature of the induced metric is uniquely determined by the Gauss curvature. And you find a formula which relates this Gauss curvature in terms of the rho, which is this one here, chi hat times chi bar hat. So chi hat and chi bar hat are defined. So chi AB and chi bar AB are two tensors which are symmetric on S of UU bar. So the symmetry is very easy to read from the definition. And you want to subtract the trace. So you write chi AB as chi hat AB plus 1 over 2 gamma AB times trace chi. Right? So this is a trace relative to gamma. Gamma is just the induced metric on S of U. So this has this induced metric. Right? So in a frame, of course, gamma is just delta AB if I have an orthonormal frame. Okay, so this is a relation between the traceless parts of the null second fundamental form and the traces of the null second fundamental form and the rho. So this is a very important equation also. Okay, finally, you have the null Bianchi. So null Bianchi means you look again. I mean, this is I said it before, but it's never wrong to repeat the same thing many times. So you look at equations like this or the other ones involving cyclic permutations of covariant derivatives, and you decompose it relative to the frame again. And you do that, you get the equations which look either like a derivative of a curvature in the direction of E4 or a derivative of curvature in the direction of E3. And of course here, this refers to an angular derivative. In other words, this is a covariant derivative on the two surfaces. The same thing here. So that's the sort of the structure that you expect by looking at equations that relate curvature with Ricci coefficient and the Bianchi equations. Okay, now let's see them let's take a closer look to the equations that you get. Okay, so you see you have a long list of equations. And they seemed complicated, but on the other hand, that's life. At some point you have to do calculations. There's nothing you can do. I mean, otherwise you don't get anything interesting. So you have to get familiar with these equations, and it turns out actually that they are not really that bad. In particular because there are lots of symmetries. Okay, so this equation is really the Raychaudhuri equation that we saw before. So it's a derivative in the E4 direction of trace chi plus a half trace chi squared is minus chi hat squared minus 2 omega trace chi. So, okay. So before there was no omega. Omega was 0. That's why this term was not present. So omega comes from the fact that E4 is not geodesic. So anyway, this is easy to deal with typically, because I can always renormalize my E4 or the trace chi to get rid of this term. So that's not that important. This, of course, is extremely important for, as we shall see, this has lots of consequences. And of course, another important thing about this equation is that there is no curvature term on the right-hand side. There is no curvature term on the right-hand side because of the Einstein equation. So the Einstein equation is Ricci equals 0, implies that there will be no curvature tensor here, right? So there is no curvature tensor in that on the right-hand side of the Ricci equation. So this is the simplest one and very important for many reasons, but we'll discuss it. Okay, then there is a derivative of chi hat in the E4 direction. So chi hat now is a 2 tensor. So it's chi hat AB plus trace chi hat AB. So you should think about it as this is a 2 tensor, this is a 2 tensor. If I take D4 of a 2 tensor, it's not quite clear what that means. The definition is that you look at it in the sense of the space-time and you project. So this expression here is projected on the 2 surfaces. So chi hat is defined only on 2 surfaces. Of course, E4 is a derivative outside. It's not intrinsic to the surface. But here, this derivative is understood as a projection on the 2 surfaces. So you take E4 and then you project on the 2 surfaces. So this is trace chi hat is minus 2 omega. This is very similar to this one. But now I have a curvature on the right-hand side. Actually, this is connected with the equation that we had before, which was, if you remember, there was a d over ds chi plus chi squared is equal to minus alpha. So d over ds is, in fact, essentially my d4. Okay? But now chi has both trace chi and chi hat here. So if I decompose chi into the trace part and the chi hat part, the trace, because of the fact that the trace of this is 0, the trace will verify the Raychaudhuri equation that we had here. And the second equation for chi hat will be exactly this one. Okay? So this is how you understand these 2 equations. Okay, then there is a derivative of trace chi in the E3 direction, right? Because I have both E4 and E3, so I should expect that I have something here also. So this equation is more complicated, and now you see curvature on the right-hand side. So this is a curvature component, rho, and of course you have many other terms, right? So it's a rather complicated expression here, but the way it is. Okay, then you have the derivative of chi hat in the E3 direction. So you get a term like this. Observe that there is a similarity. So here you have this combination d4 trace chi plus a half trace chi. Here you have d3 of trace chi plus a half trace chi bar times trace chi, right? So there are all sorts of similarities. Anyway, on here, on this side of the equation, there is this operator here, which is understood. So this is an important operator. This is understood like this. D eta is a 2 tensor obtained by differentiating a 1 vector. So this is a 1 vector on the sphere, on the SU U bar. And it has a components dA eta b plus dB eta a minus divergence of eta times delta AB. In delta AB relative to an orthonormal frame, right? So this is, otherwise it will be gamma here. Right? So you take covariant derivative, you symmetrize, and you take away the divergence. So you get a traceless. So this is a traceless quantity, as it should be, because on the left-hand side, this is a traceless quantity. So chi hat is traceless, this is traceless, this is traceless. Therefore, everything here should also be traceless, and that's what you get this. Okay? So that's what this operator is. It has a geometric significance. It's actually a very important operator, but we'll discuss maybe later. And the other terms, so this is defined in a similar way. You take eta b, eta a plus eta b plus eta. sorry, you have eta A, eta B plus eta B, eta A, and you subtract again the trace part. Right? So that's easy to define. Okay, then you have equations for eta. You have d4 of eta, and now a curvature on the right-hand side, which is the beta component of the curvature. And here, actually, you see this equation, you already realize the symmetry when you interchange E3 and E4. If I interchange 4 to E3, then eta becomes eta bar because of the definition. So this becomes C3, this becomes eta bar, beta becomes beta bar, but remember that beta bar changes sign when I interchange E3 and E4. So I get a beta bar here, and then chi bar, which is this one becomes chi bar, this becomes eta bar minus eta, and there was a minus sign here, this becomes a plus, right? So that's very simple again. And then there is an equation for d3 of omega, which again has curvature on the right-hand side and some combination of eta, eta bar, omega, omega bar, which I'm not going to write. And something similar happens here, again by symmetry. Okay, so these are transport equations, but I didn't write all of them because obviously I should have also the d3 trace chi bar equation, right? When I take in trace, instead of trace chi, I take trace chi bar, and here I should have d3, and here it should be trace chi bar, and so on and so on. But this equation I'm not writing because they are completely symmetric. I mean, once I have this equation, I automatically have the other one. So I don't have to, so this splits the total number of equations in half. Right? So the same thing happens here. This will become d3 of chi bar hat, and so on and so forth. You'll get alpha bar instead of alpha, and so on. So you get, I have 1, 2, 3, 4, 5, 6. So I get another 6 equations, right? Actually, maybe only 5, because I already have a symmetry here. And this is also a symmetry, so I don't get more. Yeah, so these are already symmetrized. So I get about 10 equations. That sounds right, 10 equations. Okay, and then I have this Kodazzi equation. Remember that we said that there are some equations, these ones here, which are satisfied on, which are intrinsic to two surfaces. So you see you have the divergence. Divergence means simply the divergence on the two, on this S of u bar, right? So it's, I have chi hat AB, and I take dB of chi hat AB, so I get a 1 form instead of a 2 tensor. So this is what I have on the left-hand side, and on the right-hand side I get derivative of the trace. I get a curvature component. This is a space-time curvature component, restricted, of course, to the two surfaces, and of course I get these other terms. The same, so by symmetry, I get immediately divergence of chi bar hat, which is this. So these two are symmetric. But there is, in addition to this one, there is another one, which is curl of eta. So curl of eta, which is minus curl of eta bar, it's easy to see, is equal to rho star plus chi bar hat, wedge chi hat. So this is this is sort of a tensor product which is anti-symmetrized here. So it's very easy to define. And of course, I have the Gauss curvature, which is this. Right? So that's how you read the non-structural equations. They are not so bad. They are not so bad, but they're extremely useful. Okay, so now the Bianchi, the null Bianchi equation. So these are the equations which are obtained, as I said, are obtained from the Bianchi by taking projections on the frame. So there is an equation for alpha. You see, this is again, alpha is a 2 tensor. It's a symmetric 2 tensor on the two surfaces. I take, again, a E3 derivative and I project. So this is a projected thing, plus a half trace chi bar times alpha. Here I get, again, this operator, which is derivative of beta in, you symmetrize and you take the trace away. So you get the traceless part, in other words. And here I have components of curvature multiplied by Ricci coefficients. So everything is a component of curvature multiplied by a Ricci coefficient. Okay, so the alpha has only a derivative in the E3 direction. Okay, so that's important. So alpha does not have a derivative in the E4 direction. On the other hand, beta, which is the next term in the hierarchy of curvature, has derivative both in relative to E4 and relative to E3. So you get two equations. This goes up. In other words, d4 of beta is now divergence of alpha, and so on and so forth. Okay, rho and rho star also have two equations. And rho also, so rho star is the sigma that we had before. So again, you have a lot of symmetries here in these equations and in these equations. And by symmetry also, alpha should go into alpha bar, E3 goes into E4. So I have an equation which I didn't write, but which can be obtained immediately from this one, which is the equation for alpha bar. So d4 of alpha bar plus straight sky alpha bar. Here beta will become minus beta bar, and so on. Okay. So again, it's very easy. If I write this equation, it's very easy to obtain all the other ones. So anyway, so this is how they are in all their glory. Now, there is something else that I wanted to show you, which is very important in order to memorize and sort of have an understanding of how the equations look like. You see, there is an issue of signature. Signature is something which is also very important. And in fact, actually, maybe it's best to look here at signature. You see, alpha was defined. Maybe I should write it. So somehow, to understand the equations, you want to understand the symmetries and the signature associated to. Okay, so what is a signature? Okay, well, I have alpha, beta, rho, beta bar, alpha bar. So this involves two E4s and then EA, EB. Right? So it involves two E4. So the angular part of the frame should contribute to the signature of this component with 0. So this doesn't give me anything. But this gives a signature of 1. This gives a signature of 1. So alpha has signature 2. Is equal to 2. Beta, on the other hand, was R, EA, E4, E3, E4. But there was a 1/2, but that doesn't matter. And now this has signature 0, 1, minus 1. E3 is minus 1. E4 is 1. So the total signature of this of beta is equal to 1. Rho was defined by a quarter R, E4, E3, E4, E3. So the signature of rho is equal to 0. The signature of rho star is also 0. The signature of beta bar is equal to minus 1. Signature of alpha bar is equal to minus 2. Right? Well, I can do exactly the same thing for the Ricci coefficient. So for example, chi was defined as G of dA, E4, EB. So the signature of this one is 1. The signature of chi bar will be minus 1. And so on and so forth. So every component of the Ricci coefficients and every component of curvature has a signature which is naturally defined. Okay, and then it's very easy to convince yourself that in any of these formula, the signature has to be preserved. So for example, the signature of this term is 2 from alpha and minus 1 from E3. So this is signature 1. This has signature 2. Chi bar has signature minus 1. So this is also 1. Beta has signature 1. And this is the angular derivative. So signature 0. And so on and so forth. So the signature is preserved. And therefore, you can easily see that certain terms cannot possibly be, if you forget exactly what is the structure of the quadratic term, for example, which are more complicated, you see that certain terms cannot be present. For example, here you see immediately that chi bar times alpha bar, chi bar hat, for example, times alpha bar cannot be present because this will have signature minus 3, but this has signature minus 2. Sorry, this has signature 0, right? So it cannot be present. So and so on and so forth. So the signature, again, is something extremely important, right? To understand the equation. Okay, so now I want to start talking about formation of Trapp surfaces just to show you how these non-structural equations, how useful they are. So we start with a theorem which is a which I mentioned earlier, Penrose singularity theorem. A space-time cannot be future null geodesically complete if the Ricci in the direction of a null vector field has to be positive. There exists a non-compact Cauchy surface sigma 0 in M. There exists a closed Trapp surface S in M. That is, trace of chi and trace chi bar are both negative at all points on the two surfaces, right? Okay, so so this already discussed. I'm just going to recall that the main thing is this Ricciarduri equation, that d over ds of trace chi plus a half trace chi squared is minus chi hat squared minus Ricci LL. This is not exactly, this differs a little bit from the Ricciarduri equations we had before because of this term, but this is just a normalization issue, so let's not worry about it, right? It's essentially the same thing. Okay, and of course, another difference with what I had before is that this term was 0 because I'm, in the previous slide, I was in vacuum, so that term was not present, but otherwise, it gives you, in fact, a good sign. Okay, so anyway, so this is basically the theorem, and everything reduces, in fact, to this equation, and a little bit of topology, but a very trivial topology which is used. Okay, so now the main issue is, can Trapp surfaces form in evolution and in vacuum? So the standard feeling that people had about formation of Trapp surfaces was based on spherical symmetry. That in spherical, I mean, there were calculations done in spherical symmetry, and in that case, you cannot talk about Einstein equations in vacuum. You need Einstein equations coupled with something, coupled with matter, which from a physics point of view is very reasonable. You have matter, and then the matter somehow is focusing in an incoming direction from all points, at all points, because you are in spherical symmetry. And somehow the mechanism of a Trapp surface was understood as being sort of focusing, coming from matter. If you don't have matter, it was not at all clear that such a phenomenon occurs. So in vacuum, the first result of the type was the result that I'm going to talk about, which is the one of Christodoulou, which is a little bit, was somewhat of a surprise because the somehow formation of Trapp surfaces was always understood as being something that has to do with matter. Of course, if you have a Trapp surface, in principle, you expect also to have a black hole, because Trapp surfaces, according to the cosmic censorship conjecture, the weak cosmic censorship conjecture that Michalis mentioned in his talk, according to the weak cosmic censorship conjecture, you cannot have Trapp surfaces outside black holes, right? So if you have a Trapp surface, you should have a black hole if the weak cosmic censorship conjecture is verified. Of course, it's a huge if, right? But somehow the belief is that it should be satisfied. Anyway, so this is the main question. So now let's talk about this. So this is a remarkable result of Christodoulou in 2008, who proved the formation of Trapp surfaces starting with characteristic initial conditions. Right? So what does it mean, characteristic initial conditions? Of course, we only talk about Cauchy data so far, right? So we always talk about development of an initial data set. You start up with initial data set and you construct a solution. But you start up, of course, with a space-like hypersurface, and you construct a solution. So this is an initial value problem, and of course, we know the result of Yvon-Choquet-Brouard. But in partial differential equations, when you have a hyperbolic equations, you can solve not only the Cauchy problem, which corresponds to space-like hypersurface, you can also solve the characteristic problem, where you put data on two hypersurfaces, two null hypersurfaces, which intersect here somewhere, right? And you prescribe data both here and here. So you prescribe initial conditions, and then for very general class of hyperbolic equations, you can show that if you have data here and here, you can construct a solution at least for some time, for a short time, right? So there is an analogous of a Yvon-Choquet-Brouard result, which tells you that you can construct a small initial data, a small solution of the initial data set. Of course, there is a question of what are the initial conditions on these characteristic hypersurfaces. In particular, what are those conditions in the case of the Einstein equation? By the way, the characteristic initial value problem was actually studied by many people, including Yvonne Choquet-Brouard. But sort of the most satisfactory result that is known is due to Randall, who proved, I don't know, about 20 years ago, he proved a general result about initial value formulation, the characteristic initial value formulation for general relativity, and showed that if you start up with an initial data set on a Cauchy hypersurface, you can construct a solution for a short time. Okay, so that's basically what was known before the result of Christodoulou. Okay, so what Christodoulou did is look at the problem not starting with space-like hypersurface. In other words, look at the formation of black hole problems, trap surfaces, not starting with a space-like hypersurface, but starting with an initial, with a characteristic initial data. So this is a picture represented here in simpler shape. So this is, there are two hypersurfaces. So this is this one null hypersurface, another null hypersurface, right? So here, Christodoulou assumes that you are in Minkowski space. So the data here is trivial data of Minkowski space. Okay? While, of course, also here, it's trivial data. But he only assumes that something non-trivial happens in this region, right? And then, you don't care about what happens afterwards because you are only interested in evolving initial data from here and here, right? So in principle, the local existence result of Randall will give you a small region where the space-time can be constructed. Or if you want to do the whole region here, you'll have a very, very small region on this side. Okay, anyway, so Christodoulou had to go much further than the result of Randall by constructing actually initial conditions here. So these, of course, are trivial. But he constructs initial conditions here depending on a parameter, which is delta, such that the data here is large in some sense relative to that parameter. When I say in some sense, it's very important because it's very, very important to specify in what sense the data is large. It cannot be arbitrarily large, right? But what happens is that a certain component of the initial data can be large here. We'll see it in a moment, which one. Okay, so you allow something large to happen here. Delta is a small parameter, so somehow the largeness is measured in delta to the minus 1, okay? Delta to the minus half maybe. Okay, so anyway, imagine that you have some data here which is large, some data here which is totally trivial, and now you want to construct the spacetime more than what Randall did. You want to construct it for a long time. In fact, something of size 1, more or less. So you want to go this way with a double null foliation. Now we know what a double null foliation is. I want to foliate my spacetime by u and u bar, both of them being optical functions, and getting a double null foliation here. The double null foliation, so the initial data will correspond exactly to u equals 0. So I have two optical functions, u and u bar. So this corresponds to u equals 0. This corresponds to u bar equals 0 here, and u bar equals delta here, right? So this delta is a small parameter. Right? Any questions? So this is the picture. And again, the data here is large, so in principle you don't expect to go very far. But he's able to show that in fact you can go quite far. You can go for something which is of size 1, as I said earlier. And then by assuming something more about the initial data on here, he gets a trap surface forming here. Right? Okay, so that's the formation of trap surfaces result. Okay, so of course we have to see what is the mechanism of formation of a trap surface. Now, it's important to note that the data, which is here and here, is such that by itself, you don't have any trap surfaces initially in the data. Of course, if I give you an initial data set which has a trap surface in it, there's nothing to prove, right? The interesting thing here is that I start with a regular initial data set without any trap surfaces, and I construct one which has a trap surface later on. Okay, so that's okay. Right. So okay. So here are some formulas which are very simple, which relate R. R, if you remember, is a volume radius of the sphere S of u bar. So it's 4 pi r squared is the area of S u bar, right? So if I have u and u bar, I have the R, and therefore I can look at the equations for dr over du bar and dr over du, and it's very easy to check. So these are very simple things to check that I get here the integral of S u bar omega trace chi, and here omega trace chi bar, right? So in particular, you see that the radius is decreasing in both directions, both in when I go in the direction of u bar and keep u constant, or when I go in the direction of u and keep u bar constant. If trace chi and trace chi bar are negative, then these quantities will be negative. So in other words, that's the situation of a trap surface. For a trap surface, both dr over du bar and dr over du are negative, right? That's the way to interpret those formulas. And they are very easy to check. Okay? So this is a triviality. Okay. So here is a plan of what I want to do. So heuristic assumptions on the future development. The future development is exactly this stuff here. Shows that if in addition to the heuristic assumptions, a uniform largeness condition is satisfied, then a trap surface must form in D, right? So in this domain of dependence. Under similar heuristic assumptions, Christodoulou's condition can be weakened, and I'm going to explain a recent result. Well, it's not so recent anymore, actually, sorry. A result of Luc, Rodniansky, and myself. And then we'll have to do the hard part to show that these heuristic assumptions hold true for Christodoulou's short pulse method. All right, so let me explain a little bit more what I mean here. So starting with initial data introduced by Christodoulou, one can construct a spacetime, and in this spacetime, I can actually show that various estimates hold true for Ricci coefficients and curvature components. Okay? But obviously, whenever I prove an existence result, I have to prove it together with lots of. I mean, in the kind of mathematics we do, you never get something for nothing. I mean, in order to prove a global existence result, you have to do it with a lot of machinery, and in the process, of course, you get a lot of control on the spacetime you are constructing. Okay, so that's these are connected with these heuristic assumptions. And of course, you have to show that the heuristic assumptions are satisfied. So anyway, so again, let me make it a little bit more clear what I said. So the proof of Christodoulou and also the proof of my work with Rodniansky and Jonathan is based on two parts. One part is to construct a spacetime for a very long time and show that that it has many properties which are going to be important in the second part. The second part consists in using those properties as some kind of heuristic assumptions now. You are allowed to use a heuristic assumption and show that the trap surface forms. The second part is much easier. Right? The second part is almost a triviality by comparison to the first part. The first part takes 500, in Christodoulou it takes 560 pages. And the formation of trap surface, the second part, takes about 10 pages. Right? Unfortunately, in Christodoulou's book, you find those 10 pages at the end. Right? Which is, so you have to read the whole book before you see how the trap surface forms. Right? Okay. Fortunately, I mean, in more recent results, usually the way we do it, we always put it at the beginning, right? So you first show how the trap surface forms, and then you justify the heuristic assumptions which are made in the. Okay, but let's talk about this now. Okay, so these are the heuristic assumptions. So remember that we have Ricci coefficients, right? So again, we are talking about we are talking about a region like this. So this is u equals 0. This is u equal delta. This is u bar equal to 0. I'm sorry, the other way around. This is u equal to 0. This is u bar equal 0. This is u bar equal delta. Okay? So in other words, these are the incoming hypersurfaces. This is the outgoing hypersurface. And we have a double null foliation here. Right? So we have this double null foliation. Right? So to this double null foliation, we have Ricci coefficients. So I can write down all the Ricci coefficients. And the claim is that these Ricci coefficients, so the heuristic assumptions, which I'm going to make, and these heuristic assumptions are proved in the first part of the theorem of Christodoulou. So the heuristic assumptions are that omega is like 1. That's natural because 1 is the value of Minkowski space. But with something which is, with an error which is of size delta to the 1/2. Right? So in other words, as delta is small, this error is very, very small. Chi hat, on the other hand, so this is sort of the main point, this chi hat is delta to the -1/2. So chi hat is huge, right? So this chi hat is responsible for formation of sharp surface later on, as we shall see. So this is this is also tied, of course, with initial conditions. The initial conditions that Christodoulou takes is such that chi hat is large. Okay, omega is also big. It also looks like delta to the -1/2. This is, of course, yeah, so this follows also from the analysis of the first part, in the first part of Christodoulou's result. Tres chi and eta are of 1. Okay, so in other words, they stay bounded. It's very important, of course. And chi bar hat and tres chi bar plus 2 over r. Again, this is a value in Minkowski space. So this is 0 in Minkowski space. Chi hat is 0 in Minkowski space. Omega bar is 0 in Minkowski space. And of course, the assumptions we make is that they are all like delta to the 1/2. Then angular derivative, these are angular derivative in S of eta is delta to the -1/2 plus something small, a small constant here. Okay, so this is again a very important assumption. You see, this expression here is large relative to delta. And then according to the formulas we had here, it's very easy to check that dr over du is like -1 plus O of delta to the 1/2, and r is like r0 plus u bar plus O of delta to the c. r0 is a value here. So r0 is a value of r here at this corner of the space-time you are constructing, right? So you have initial data here and here. This is the trivial initial data. You have initial data non-trivial here, and that's a corner, which corresponds to, sorry, this is r0, excuse me. So r equal r0. Okay, r equal r0. Okay. Right, so all these are trivial. Once I have this, it's very easy to prove these ones, of course. Okay, now you look at the whole Ricci equations, right? The whole null structure equations. So there are many, as we saw. But among those, Christodoulou uses only 2 equations. This one, d4 of tres chi plus a half tres chi squared. So this is the Ricciarduri equation. No curvature on the right-hand side. And the other one is this 3 of chi hat, derivative of eta. So this is a complicated term here. Again, no curvature on the right-hand side. So they are both equations which are implied somehow by the Einstein equations. It's because of the Einstein equations that there are no curvature terms on the right-hand side. Okay? Okay, so these are the 2 equations that Christodoulou is using. Now, using the assumptions which we made here, it's very easy to see that d over du bar of tres chi, so again, derivative with respect to u bar are derivative in this direction, right? So u bar is a derivative in this direction, like it's like a E4 derivative, right? So d over du bar of tres chi is minus chi hat squared plus a term which is delta to the -1/2. So that's very easy to see from the fact that omega behaves like delta to the minus a half. So you have this term here, which trace chi is bounded and so on. Okay. Remember that in order to show that a trap surface forms, actually, I mean, I should point out, this is very important. I want to show that a trap surface forms somewhere here. I mean, maybe even earlier, but it forms somewhere. Of course, once I have a trap surface, it's easy to see that I'll get many more trap surfaces beyond the first one. So the fact that I get a trap surface, that means the trace chi here should be negative. Right? So that's what I really want to prove. I want to prove that trace chi is negative. It starts by negative at every point, right? So this is the two surface. It has trace chi will be negative at any point on these two surfaces. So it's obviously extremely important to keep that in mind. Okay, so now I get this equation minus 2 omega trace chi, which I use this assumption. So I get rid of this term. And also I get rid of this term. Sorry, there are two. This one should not be there because I already put it here. Okay. And then from this equation, I have derivative of eta behaves like delta to the minus a half plus a little bit more. C is a small positive constant. And similarly, all the other terms. If I look at what I get, this is what I get. I get the d over du bar trace chi is minus chi hat squared plus O of delta to the minus a half. D over du of chi hat squared plus trace chi bar chi hat squared is O of delta to the minus 1 plus C. Right? So this is from the right-hand side. The right-hand side of the second equation was very complicated, but somehow, because of the heuristic assumptions, I can make it very simple. Right? See, normally, an equation like this is almost impossible to solve because, you see, everything depends on everything else. Chi hat depends on eta, depends on omega. Omega, of course, I have to look at the equations verified by those, and so on and so on. I mean, you never close. So the genius of Christodoulou here is to pick up exactly the right assumptions, which allows you to get the mechanism for formation of a trap surface. So anyway, so this is what it is. Okay, so now you see these are simple ODEs now. I can just integrate. So I integrate the first one, right? So I get immediately that, well, initially, of course, trace chi at u and 0 is 2 divided by r of u and 0. This is just the initial data. Right, when u bar is equal to 0. So this is just the initial data here, right? So this was Minkowski space. So obviously in Minkowski space, the value of trace chi is just 2 over r. So this is what is expressed here. So trace chi, therefore, trace chi of u bar is 2 over r minus integral from 0 to u bar of this term here. And plus, I'm integrating from 0 to u bar. The length of this is delta. So delta times delta to the minus a half gives me delta to the 1/2, right? Which is a small term, fortunately. So this is an error term, which is small. So I will be able to neglect later on. Okay, now from this equation, so this equation, of course, comes from here by multiplying, I forgot to say, you multiply this by chi hat. So that's why you get d3 of chi hat squared. But d3 is the same thing, essentially the same thing as d over du. So that's why I get d over du here, chi hat squared plus trace chi bar, chi hat squared equal to this. So now I multiply this by r squared because I know that trace chi bar is like minus 2 over r. Again, trace chi bar is minus 2 over r because of my assumptions here. You see, trace chi bar plus 2 over r is small. So, so I'm allowed to multiply this by r squared and then integrate this ODE and get the d over du of this is equal to r squared. This plus this is equal to r squared O of delta to the minus 1 plus a constant. Therefore, you get immediately that r squared chi hat squared at u and u bar. In other words, I'm looking at some value here, can be expressed in terms of the value at this point. Right? So whatever is here, I can express it in terms of what's there. So, so you see, you get this very simple formula. Okay, now R of u and u bar, as we already saw, is R0, which is the value here, plus u bar minus u. So this follows immediately from the equations we had for du of R of u bar and du bar of R u bar. Right? So this is again something very simple that follows from the heuristic assumptions. And therefore chi hat square evaluated at u bar is R squared of 0 u bar divided by this, and so on and so forth. Anyway, so these are all trivial manipulations. You get finally, okay, so now obviously what you want to get is to include this term here. So you want to use, so okay, maybe I should say a little bit more about the philosophy of the proof. Because I'm going maybe a little bit too fast. Okay, so you see, if I were in Minkowski space and I would look at just the same kind of picture in Minkowski space using the standard double null foliation, then chi hat will be 0. There is no chi hat, right? So this term will be 0. I'm sorry, maybe I should go a little bit before. Right, so this term will be 0. Omega will be 0. This term, of course, should not be present. You get just this, or you get rather d4 of trace chi is minus a half trace chi squared. Well, this, of course, has a sign which is nice. It's a negative sign. It shows that trace chi should decrease. But of course, I cannot get a trap surface out of this equation because obviously it will be inconsistent with what happens in Minkowski space. Because in Minkowski space, if I look at the null cone from a point, of course, trace chi verifies exactly this equation. ds trace chi is plus a half trace chi square is equal to 0. But of course, there is no trap surface here. Right? I can't get a trap surface in Minkowski space. I mean, it would be a disaster if I could. Right? So, if you just look at this equation in Minkowski space, you can't do anything. And also, that means that somehow just using this equation, I cannot do anything, even though this term has a good sign, right? So it drives trace chi to become more and more negative, right? I mean, it starts positive, it drives it towards smaller and smaller, but I cannot make it negative using this equation, right? So, Christodoulos' idea was to show that this term is big enough, right? So that it actually drives things towards a trap surface. So it actually makes trace chi negative. But in order to do that, you have to analyze its behavior, and that's why he's using this equation. Of course, this equation was extremely complicated. By the way, this equation was very easy in spherical symmetry. So in spherical symmetry, you could do it. Of course, in the spherical symmetry, you had to have additional matter and so on. But in principle, this you could do. And of course, Christodoulos knew this very well from his work on spherical symmetry. But in general, this is extremely complicated. And nevertheless, by making these assumptions, you essentially reduce all those terms to nothing, right? I mean, they're just error terms. Of course, in a first approximation, they are delta to the minus 1 plus c, but you'll integrate later on, and this delta minus 1 disappears. OK, anyway, you put everything together now, and this is what you get. You get the trace chi of u and u bar is 2 over r u0. So this is a term that came from here, right? So this was this term. And now this term here you estimate using the second equation. And you get, as a consequence, you get this term. Okay? And delta minus 1 plus c, because you integrate from 0 to u bar, that term which was delta to the minus 1 plus c becomes delta to the power c, right? Which is a small term again. And therefore, now, to make trace chi negative, I just have to make this quantity negative. But, I mean, you get a very simple condition. You get the infimum of integral from 0 to delta, in other words, integral from 0 to here, of the chi hat 0 at u bar and omega. Chi hat 0 is just the initial data of chi hat, I should have said. So here, you prescribe this chi hat 0, right? So this is prescribed. Okay, so you prescribe this. So you have it completely under your control, this quantity. And you want that infimum of this should be larger than, right? So this is just exactly the condition that trace chi is negative. Trace chi is strictly negative, it's exactly this condition. There is another condition here which simply says that, there can be no trap surfaces initially. So this condition on the right is just the condition to ensure that there are no trap surfaces here on the initial data. In other words, chi hat 0 is such that you don't have any initial trap surfaces. All right? So that's all that is to it. So, so if this condition is satisfied, you form a trap surface. Okay? And now, of course, this is something that you can work with. So if U is sufficiently, if U is sufficiently large, R0 is fixed, I take U sufficiently large, obviously I get the trap surface, right? Okay. So that's a mechanism of formation of trap surfaces. Of course, now obviously you have to show that these heuristic assumptions are verified. In other words, there exists a space-time which verifies these assumptions. But that's later. So let's now go very fast over the result of Rodniansky and myself. Okay, I have very little time, unfortunately. So I get so the only difference between Christodoulou's result and our result is that in Christodoulou's result, you see, he's looking for a trap surface among this family of S of U and U bar. Right? So this is a family given by the double null foliation. So it's an intersection of U and U bar. And the trap surface has to be exactly of this type. So what, and of course I guess I didn't say, but you see, when you specify this condition has to be verified at all points. So you see, there is a uniformity condition here. In every angle omega, this integral, so this is an integral along an geodesic, of chi hat with respect to U bar, du bar has to be large, right? Larger than this. That means that somehow the initial data has to be uniformly large in all directions, right? Along all null geodesics, this has to be large. In particular, of course, I cannot take chi hat to be 0 at some point, right? I cannot take initial data. So again, the initial data, obviously, when you consider the initial data, you should think about an outgoing light cone, right? So you are talking about an outgoing null cone. This is your U equals 0. And you are prescribing data here. You are prescribing this chi hat 0. It turns out that when you solve the characteristic initial value problem, this is exactly the quantity that you can freely define. I mean, freely prescribe, sorry. There is no constraint on this. I can just take it whatever I want, and I'll construct a solution based on this, right? So that's a very important fact. So this is free. But the condition of Christodoulou now is that this quantity should be large in all directions. In other words, it should be large everywhere here, right? In all possible directions. Now, the result of Jonathan, Igor, and myself is actually to prove that, in fact, you can replace this condition by a condition which is localized only along a null geodesic. So I have to take something large, which is like here, but only in a neighborhood of a null geodesic, and I still get a trap surface. Okay? So in other words, I can take something large only in a neighborhood of a fixed null geodesic, let's say this one, but I can take chi hat 0 everywhere else, chi hat to be 0 everywhere else, right? It's large only in a, so this is highly unintuitive, right? Because a trap surface is something that is large everywhere. I mean, it has a sign everywhere. There's a negative sign everywhere. And yet, in this result, you are starting with something which is actually Minkowski essentially everywhere except in a neighborhood of a null geodesic. Right? Okay, so how do you do that? The idea is that actually you use the heuristic assumptions of Christodoulou. So in other words, you use the first part of his result, but you do a little bit more work. So here's what you do. You look, you see, so this is sort of the initial light cone. And I need to move inside, right? So moving inside means moving along these directions, right? So I'm moving inside. Now, the double null foliation will be an intersection between this and the U bar corresponding to this, and then U, another U which goes this way. But let me not draw it. Okay, so Christodoulou is looking for trap surfaces of this type. Instead, what we are going to do is that starting with our initial data here, we are going to construct a deformation which becomes trapped later on. So I start up with initial data here and construct a deformation of the original surface here, which is not attached anymore, of course, to the double null foliation. It's a completely different foliation. Right? So the final result will not look at all like this, but will look rather than like this. I don't know, a trap surface will look much more complicated. In fact, you don't have a local description of the trap surface, but you can prove that such a thing will form. Okay, so let's see how does this go. Well, the idea is to look for deformations. Right, so we look for, we have this double null foliation, you have the omega, you have trace chi, theta, and so on, all the Ricci coefficients. You look now for foliations of the type V of U and omega. And in fact, you take the derivative of V with respect to U to be e to the f, where f verifies an equation like this. Anyway, there is a little bit, I probably will not have time to go through the details. Let me just simply say that there is a way of prescribing a new foliation somehow along a null cone, along a fixed null cone. I can prescribe a new foliation, a foliation which is very different from the original one, which allows me to get to a trap surface. So here is how, relative to a change of frame. So again, this is a change of frame. How should I say it? So if I have a null hypersurface, and I have one foliation, I can define a different foliation by specifying sort of a function as here, specifying this function f. Okay, so a function f which is prescribed originally. So I prescribe a function f which gives me a speed of the foliation, and doing what I'm doing here, I can construct a deformation of the original surface of this original surface, a deformation along the null cone, which is very different from the original foliations which I had. The original foliation could be viewed as being just L of s is equal to 1. So L is for example, the geodesic vector field associated to the null cone. L of s is equal to 1 is the affine, so s is the affine parameter of the original vector field. But now I construct a different foliation. Anyway, to make a long story short, you can calculate the trace chi prime of the new foliation in terms of the old foliation, and of course the speed f with which I have defined the new foliation. Okay?
But the new foliation is still space-like that?
Yeah, of course. So it's a foliation on a null hypersurface, so it is going to be space-like. Okay, so this is what it is. It is a complicated formula, but it's easy to analyze because I already know these things. I already have good information about these expressions from these heuristic assumptions that we used in the proof of Christodoulou theorem, right? So because of this, I can calculate, you see, I can calculate trace chi prime. It looks like this in terms of the delta, right? In other words, if I'm using the fact that I know trace chi bar, I know chi bar hat, I know eta, I know theta, I get a simpler expression looking like this. Well, this is a Laplace-Beltrami operator on F0 on the two surface. So this is a Laplacian on two surface. Now, from the calculations of Christodoulou, I already know that trace chi looks like this. All right? So all I have to do is to go from trace chi to trace chi prime, and I find that trace chi prime now looks like this, where M0 is exactly this integral that we saw also in Christodoulou's work, integral from 0 to delta of chi 0 hat squared of u bar prime, right? So this is the original, exactly the same quantity as in Christodoulou, which comes up here. But now I have a new term, which is rather complicated. It's non-linear in F0, as you see. You have gradient of F0. So this is F0. Again, F0 is just a function defined on, say, the original two surface, which I have. Right. So, okay. So anyway, so again, to make a long story short, in order to form a trap surface, the condition that I need now is this one. That if I introduce R as being 1 minus e to the minus F0 plus O of delta to the 1/2, and I think of R as being a function of F0 along S0. So F0 is a function, sorry, R is a function of the original F0 on S0. Then R itself, the condition of a trap surface now looks like this, that minus Laplacian of R plus R minus 1 gradient of R squared plus R is less than M0. And therefore, what I need is to function R such that, right, so I should think about, yeah, I mean, this is a bit awkward the way I wrote it here. So I go from F0, I go to R, so I prescribe R now. So I have to think about R as being a function prescribed, which I can choose. But it has to satisfy, in order to get a trap surface later on, so in other words, in order to get a trap surface somewhere here, right, a complicated trap surface somewhere there, I need to satisfy this equation initially. So R, the choice of R, has to verify this inequality, where M0 is again that quantity which we encountered before. Okay, so if you analyze this equation by taking R to be e to the minus phi, you derive an equation looking like this. Laplacian of phi plus 1 is less than M0 e to the phi. Again, M0 is that quantity, the Christodoulou's quantity. And you see, for example, from this inequality that if M0 was 0, in other words, if you are in Minkowski space, M0 is 0 in Minkowski space, right? Because chi hat will be 0. Then you'll get Laplacian of phi plus 1 is less than 0, which of course is never satisfied, because if you integrate, you get 0 here by integrating. And of course, 1 gives you something which is positive rather than negative, right? So this will never be satisfied in Minkowski space. But if you are not in Minkowski space, and I can construct an M0 for which this inequality is verified. So I have to satisfy, you see, I have to verify a non-linear elliptic inequality. Okay, so I have to find, in other words, a phi, verifying an equation like this. And it turns out that this can be done by a simple condition on M0, by saying that M0 is large, but only in a neighborhood of a geodesic, of a null geodesic. And that's a condition which allows you to form a trap surface. So anyway, I think I went a little bit fast over this. Maybe I'll say a few more words next time. But the idea, you see the idea is to construct a deformation starting with the initial data. The deformation is not in the direction of the double null foliation. It's a different deformation. It's specified by a function R, which verifies an elliptic inequality, which is the one that we saw before. And then by doing a little bit of analysis, it's easy to show that if M0 is different from 0, I can always solve this inequality. And the result you get is something like this, right? So in other words, the surface S1 must be trapped for sufficiently small delta if M0 verifies an inequality like this in a neighborhood of a geodesic. Okay? So again, chi hat 0 can now be 0 everywhere else except in that neighborhood. Right? Okay, so with this I'll stop.